Hey guys, and welcome to another installment of Marvelous Mechanics. In today's episode, we will be discussing the principle of moments. Let's take a look at this beam. It is supported by a roller support and is loaded with the force F at its right edge. In theory, this force would rotate the beam around the support. We can also represent this turning force as a moment about the support in our sketch. The magnitude of this moment can be calculated by multiplying the force with its distance from the pivot point. Let's apply what we've learned on a little example. We need to express the unknown lengths and the support force as functions of the given quantities. Since we are now familiar with the concept of moments, we can predict F2 would rotate the beam clockwise about the roller support. F1, on the other hand, rotates the beam counterclockwise, which is an important distinction we must make. We can now replace the symbol for the roller support in our sketch with the vertical reaction force that the support can accommodate. Next, we write down the equilibrium conditions for the static system. For the moment condition, we consider a counterclockwise rotation about point P to be positive. Force A rotates counterclockwise about point P. Therefore, we denote it as positive in our equation. Because F2 rotates clockwise, the moment generated by the force at the point P is recorded as negative in our equation. Since this is a static system, the sum of all moments must equal 0. Otherwise, the system would rotate. Let's rewrite the vertical equation to express the support force as a function of our two given forces. We can rearrange the moments equation as well. Notice how we can substitute the expression for A from the vertical equation into the rearranged moment equation. Now we have already defined two of the three unknown quantities. Now, the only missing one is the length B, which we can simply read off from the sketch. Here is a much more difficult example. This beam is wedged between two walls and is held by a rope. We now need to determine the contact forces of the walls, as well as the rope tension, given the beam's length and weight force. We replace the walls with the contact forces in our sketch. Additionally, we replace the rope in our sketch with the rope tension that it exerts on the beam. To complete our free body diagram, we now also include the weight force of the beam, which acts at its center of mass, i.e., in the middle of the beam. In order to set up consistent equilibrium conditions, we now draw in the coordinate system to which these conditions refer. Since we have three unknowns, we naturally need three equations. But, as you can see, we still need to complete the moment condition. We see that Q rotates counterclockwise about our chosen pivot point. Yet, Q's lever arm is still to be defined. Since the lever arm of a force is the shortest distance from its line of action to the pivot point, it is clear that Q's lever arm is not L, marked by the red line, but much rather the distance marked by the green line. Since we still don't know the length of the green line, we simply consider this triangle and try to determine the distance using trigonometric functions. Since we know that cosine is the ratio of the adjacent side to the hypotenuse, and we know the cosine value for the angle pi4, we can easily determine x. Now that we have determined all the information about Q's rotational direction and lever arm, we record the moment that Q induces at the pivot in the moment equilibrium equation. We see that the weight force rotates clockwise about the pivot. We need to keep that in mind. Also, the lever arm must be determined first here as well. For that, we follow the same strategy as with the lever arm of Q. Since G rotates clockwise about the pivot, we must record the moment generated by G as negative in the equation. Force R rotates just like Q, counterclockwise about the pivot. However, the lever arm must first be determined through geometric considerations. Just like the moment induced by Q, the moment induced by R is also recorded as positive in our equation. Just as in the previous example, the sum of the moments must equal 0 here as well. With these three equilibrium conditions, we can determine the three unknown forces. For example, the rope tension S can be determined by rearranging the second condition, knowing the value of the cosine term. We rearrange the first equation for Q. As you can see, we can now substitute the expression for S from the second equation into the first equation, which brings us one step closer to having Q fully defined. Next, we rearrange the third equation for R. As you can see, we can substitute the expression for Q from the first equation into the third equation, leaving only one unknown, namely R. After some clever factoring and simple rearrangements, R is now fully defined in the third equation. Now only Q remains. To determine Q, we substitute the expression for R from the third equation into the first equation. Finally, we combine the two G terms and have expressed all the unknown forces as functions of the given gravitational force G, thereby successfully solving the problem. Let's summarize what we've learned today. First, M equals force times lever arm. This basic formula explains how torque is produced. Second, you choose the pivot and decide which rotation direction is positive. Third, in static systems, all moments sum to 0, ensuring equilibrium with no rotation. Fourth, the lever arm is the shortest distance from a force's line of action to the pivot. Thank you for watching, and feel free to leave a like, subscribe to my channel, or share this video with a friend. See you next time at Marvelous Mechanics.